G'day viewers. In this segment we'll learn about fair queuing, one of the building blocks for quality of service. So our topic is sharing bandwidth between flows, one of the key topics for quality of service. What we're going to learn about in this segment is fair queuing, or more specifically weighted fair queuing, which is one of the key building blocks for quality of service and an alternative to the FIFO queuing that we've seen up until now. Well, let's start with FIFO queuing to make sure we understand it before we improve on it. With FIFO drop-tail queuing, packets are queued in first come, first out order, first come, first serve, it's sometimes said. It's essentially a regular queue, as you and I know. The queue also has a rule that new packets are discarded when the queue is full. You could discard packets in the queue or packets, the oldest packets or something like that. But typically what's done is that you discard the newly arriving packet when the queue is full. And this is the typical queuing model or scheduler which is implemented in routers today and widely used in the internet. When we share with a FIFO queue, what's really happening is that multiple different users, or really we'll typically talk about flows of traffic. A flow of traffic is a series of related packets that come from a user, and usually they'll represent some kind of application, some meaningful application unit, such as a Skype video call, or a BitTorrent session, or web surfing by a user, or something like that. So I'll use that word flow, you'll see will come up often. At any rate, these flows all are trying to go to the same output link, which is run by a FIFO scheduler. What's going to happen? Well, we sort of know what's going to happen in that this is what the best effort internet service is all about. We have to, apps have to compete, and their traffic, the flows, will share the bandwidth and delay and loss via this FIFO queue. So if we sort of revisit it from our point of view right here, what I would say is that the bandwidth allocation, you see how much bandwidth a different flow gets, depends upon the behavior of all of the flows. It depends upon everyone's behavior. To describe this picture, on the left-hand side we have the inputs. These is actually, it could all be coming in on one link or more, but it consists of multiple different flows. And I've logically separated the traffic from three flows, the grey flow, the pink flow, and the blue flow, so you can see there's traffic from all of them, but they're all flowing in. And what will happen inside the router is they'll all be queued in a single FIFO queue for transmission onto the output link on the right-hand side. The order in which they're queued is the order in which they will arrive. And it just so happens here that it happens to be pink, pink, grey, pink, pink, blue, pink, pink, blue, and so on. That's just the arrival order that happened to be here. This means if there's a lot of pink traffic and some of the blue traffic might miss out, it just depends. Now, over the long term, how much bandwidth of the output link the different flows get is going to depend on how they implement TCP, and they share the bandwidth over the long term. Different flows are also going to cause other flows amounts of delay and loss. Even TCP sharing, it's certainly only sharing over the long term, because in the short term you could get lucky or unlucky. And even over the long term, TCP has what is called an RTT, or round trip time bias. Flows with a short RTT tend to get more bandwidth than flows with a large RTT because they react more quickly. The upshot of all of this is that the behavior that one flow sees, the bandwidth it sees, depends upon the behavior of everyone else. And if there's an aggressive user or flow in here, or more than one, they can easily crowd out another well-behaved flow so that it can get less bandwidth and see more delay and loss than otherwise, maybe than it should if it's not been aggressive in the network. What we want to do now is come up with a better way of queuing to improve fairness. And I'm going to start looking at that way of queuing by talking about what I'll call round-robin queuing. With round-robin queuing, the idea here is that instead of keeping one big FIFO queue, we're going to break the queue up and have a different queue per flow. So if I have three flows here, then I have three different per flow queues. And as my inputs come in, I will put them into the right queue, into the flow 1, the flow 2, or the flow 3 queue. So now we've split up that one big flow inside the router to many smaller that one big queue inside the router to many smaller queues. What I'm then going to do for the output link, here's the output, is I'll go round and round these queues. Every time I have an opportunity to send a packet on the output link, I'll take from the next flow in turn. Maybe I'll draw from flow 1 and then 2 and then flow 3, then go back to flow 1, 2, 3, and so on. And I'll look every time it's an opportunity to send a packet. If there is a packet there in the flow queue that I'm meant to be looking at, great, it will get sent. If that flow queue is empty, though, I'll just advance on to the next flow queue, and eventually we'll go around and come back, and then hopefully there'll be a packet from the other flow. The queue could be empty simply if there's a flow that's not sending very much traffic. Well, let's see what's going to happen here. What I really want to do is work out the output order. Well, actually, it shouldn't be too hard, so let's just think about it. If I go round robin, I should get a packet from flow 1, and then flow 2, then flow 3, then flow 1, then flow 2, then flow 3, and so on. So on the right hand side, I have the earliest one or the first one sent. And we're just going to keep repeating. So I don't even need that question mark because it's fairly simple here. So that's what we should see. Let me just clean that up. And we have that graph. Now I have gone through and done the same thing. Actually, my writing on the previous slide wasn't quite correct because I only had 2 grey packets. So if I go through and label it, I've got 1, 2, 3, 1, 2, 3, and then I have no 1 because I have no other grey packets. So I get to send flow 2 and then flow 3. Then I have no flow 3 packets, so I just send packets from flow 2 onwards. And eventually more packets should arrive. Now, one thing to note is that the output order is now no longer necessarily the arrival order. It won't be, in fact, if the link is busy and there's some amount of queuing. We can't see the arrival order in this picture. It could have been not quite anything, but we can't see whether all of those pink packets arrived all at once or not. In this picture, we could imagine, if you like, that all of the packets shown there arrived at time 0, and then I'm drawing the order in which they're sent. And again, this end is the first away on the output link. So you can see this pattern is different than the previous pattern with the FIFO one, in that we have improved the fairness in some respect. If you consider a packet at the beginning of the grey queue now, it really doesn't matter whether all of these packets came before it and are just hanging around or not. This packet at the head of the grey queue isn't going to have to wait for a large number of pink packets to go through. It will get to go through every time around the cycle. It will have an opportunity to send. So it's fairer. These flows which are sending less traffic are now seeing less delay and less loss caused by a flow which is sending a lot of traffic. So that's this point. It's better. So flows no longer see uncontrolled delay or loss, is how I stated here, from the other flows, even if those other flows are very aggressive. So even if another flow, if you like, you could consider that flow 2 here goes berserk. Flow 2 goes crazy. Even if flow 2 goes crazy, it really can't slow down traffic from flow 1 and flow 3 going out the output link. If there is a packet from flow 1 or flow 3 waiting in their queue to go, they will get to send 1 packet every 3 output packets, regardless of whether flow 2 goes crazy or not. So this is definitely a step in the right direction in terms of fairness. However, it can be quite imbalanced. So if our goal was actually to divide the output bandwidth of that link, maybe it was a 150 megabit per second link and we wanted to give 50 megabits per second to 3 different users, we haven't really succeeded with that goal. And the reason is because we haven't factored different packet sizes into account. It's the case that this wouldn't matter if packets were all basically the same size, but it's the case that packets can be significantly different in length. You might have 40 byte small packets carrying different samples, or 1,500 byte larger packets, or even more depending on the network technology. So this is 1 to 2 orders of magnitude difference. So we can easily be talking about dividing the bandwidth not into thirds, but giving someone a 30th part or a 300th part instead of a third, which is really not what you want it to do. So what we're going to do, and I've now finally gotten to the fair queuing part of this, is we will introduce what's called fair queuing. Fair queuing is an improvement on our round robin queuing, which was a straw man, if you like. And what fair queuing is going to do is approximate bit level fairness. So this really will allow us to roughly divide 150 megabit per second link into 3 50 megabit per second links. What we'll do is we'll come up with different rules instead of taking one packet from each flow queue in turn. Instead, for all of the different flow queues, we will approximate a virtual finish time for the packet at the head of the queue. We'll compute it. And this finish time will be in terms of a virtual clock. The virtual clock is defined to be a clock that ticks once when all of the queues which are non-empty have gotten to send 1 bit. Why? Well, we'll just find that this is a simple way of thinking about it that's going to give us the right order in which to send things. So we will send packets in the order of their virtual finish times. If you have a lower virtual finish time, you should get to go first. However, we're not going to aim for perfection in approximating fairness. In particular, we're not going to preempt packets that are being transmitted. So if I have a big packet that's been transmitted of 1500 bytes, and halfway through it a small packet comes in, and because it's very small, maybe it has an earlier virtual finish time, I'm not going to stop or abort the transmission of the 1500 byte packet just so I can send the small one. I'm going to send complete packets at a go. Okay, all of this might sound a little mysterious, but let's just try and work through the formulation and an example to see how it would work. To do that, I need to present you with a bit of notation. Here's the notation. So let us define arrive J of F to be the arrival time of the jth packet for flow F. Length of J of F is the length of that packet. And then the thing we're trying to, so that was length of J of F, and these are just inputs, these first two. What we're trying to compute is the finish time for J of F. Now, this looks like a little bit of a complicated formula, but it's not too bad. Let me work through it. If you just ignore the max operation and the arrive for a start, then we're saying something like the finish time of J of F is the finish time of J minus 1F, the finish time of the previous packet that is, plus the length of the current packet J of F. Well, that makes sense, because we said this virtual clock ticks once every bit is sent from every packet that is waiting, from every queue that is full. So you get to send 1 bit from your queue every tick of the virtual clock. So if you've got a packet that's length bits long, it's going to take you length ticks on your virtual clock to send it. So the finish times are advancing by the length of the packet. But what's this max operation all about? Well, the max operation just says we're going to take that length of the packet for virtual clock ticks, and we're going to start from either the finish time from the previous packet or the arrival time of the current packet, whichever is later. The reason for that is that if you think about when the packet is going to get sent, we can't start sending its bits until either the previous packet was finished. If it arrived early, it just has to wait around and it won't even get to be sent, or shouldn't even be considered until the previous packet is gone. Or if the queue was lying idle, the finish time of the previous packet wasn't really relevant, we just start again when the new packet comes. You don't get any sort of credit for not having used the queue for a long time. Let's talk about an example to try and work that out. So let's suppose for this concrete example, here are our flows again, flow 1, flow 2, flow 3. Now I've drawn the same picture so the packets look the same size, but for fair queuing here, let us consider that flow 1 and flow 3 are sending 1000 byte packets, whereas flow 2 sends small packets of 300 bytes each. If this was round robin queuing, we would take 1 packet from each queue in turn, 1, 2, 3, 1, 2, 3, 1, 2, 3. But we're trying to take the packet sizes into account. So what will fair queuing do? So we want to work out the output order here. Well, here's first again. Well, what's it going to be? To do that, we need to compute the finish times. That's how we determine the output order. Okay, let's have a go and try and do that. To do that, we'll start with the finish times of, I'll just define finish of 0 for any flow to be 0. So we're just going to start everything at time 0 on the virtual clock. And I'm going to assume that all of the queues always have something to send. So the terminology for this is that the queues are backlogged. There's always something in it. So we never just have an empty queue, we're waiting for things to arrive. If you like, you could think of this as just all of the packets in the queue for a flow just all arriving at once. Or it wouldn't actually make any difference as long as the next packet arrived before the previous packet had been fully sent, so there was always something in the queue. That's this condition here. It doesn't matter other than us just thinking that there's always a bit to send. There's always a packet to send in each of the different flow queues. Okay, let's compute the time for finish 1 F1. That is the finish time of the first packet on the first flow. Now the finish times are just the finish times of the previous packets plus the length of the packet. Since the queues are always backlogged, this max condition with the arrival is not going to come into play just yet because there's always something to send. So the finish time of the first packet will be 1,000 because it's 1,000 long. And then the second packet will be there and the finish time of the second packet will be 2,000 in our virtual clock ticks. You get the hang of this, I bet. For the finish time of the first packet of the second flow, well, it will be 300 because it's 300 bytes long. Starting from 0, you add 300, you get that. The finish time of the second packet in that flow will be 600, then 900. We're adding another 300, and so forth. And similarly, the finish times for the third flow are going to be the same as the finish times for the first flow because those flows had packets of the same size. And again, the arrival factor doesn't matter here in this particular example because the queues are backlogged, there's always a packet to send. So look at these arrival times, look at these finish times, and we're going to send packets in order of the finish times. So can you see what order we'll send things in now? Looks like we're going to send the lowest one is this one, then this one, then this one. So that means 3 packets from flow 2, and then let's say this one and this one, they're the same, so the order doesn't matter. A packet from flow 1 and a packet from flow 3. Then this one, and so forth. If I draw that as a picture, it should make a little more sense. This is the first end, and you can see we're sending packets from 2, 2, 2, 1, 3, 2, 2, 2, 1, 3, 2, 2, 2, and so on. This is what we want to do, in fact, for fair queuing. And the reason for this is flow 2 has the smaller packet, so it should get to send about 3 1/3 packets before anyone else gets to send one of their packets. And that's actually exactly what's happening. In this example, you could work it out fairly easily, just because I said the flows were always backlogged and the numbers were fairly clear. In a more complicated example, the fair queuing expressions would tell you the order in which packets should be sent so that they will always remain approximately fair. However, before we get there, I need to introduce just the final bit in this formulation, and that is to take us to weighted fair queuing. In fair queuing, what we've seen so far is a way of dividing the bandwidth of a link into n equal portions when there are n flows. We can also split it up into n slightly different portions if there are flows where some of the flows don't have packets waiting at a particular time. Then the arrival factor would come into play. But so far, all of the different flows have been treated equally. With weighted fair queuing, we generalize fair queuing. This turns out to be useful so that we can assign a weight, or an importance if you like, to each flow, each different flow. So all of the flows can have a different weight. A higher weight gives you more bandwidth. So for instance, if you have a flow of a weight of 2 for your flow, then you get twice the amount of bandwidth. You're going to get to send twice as many bits over the same period of time as the flow with weight 1. And so you can see how we can prioritize things using this weight, relatively prioritize them. To do this, we need to update our formulas for computing the finish time. And the only change we need to make is this change shown here in pink. We need to factor in the weight. So what we do is we take the start time at which we can start sending the packet, and instead of adding the length, we add the length divided by this weight. This weight is a normalizing factor. If the weight were 2, it would mean you get to send 2 bits every virtual clock tick. So instead of adding length, the number of bits we want to send, we'll add length divided by 2, because that's the number of virtual clock ticks. So using the weight factor in this way normalizes everything in terms of the virtual clock and helps us understand what's going on and the order in which to send things. Well, here's a more complicated example. I'm not going to work through it now in this short lecture, but it's an example. It's taken from your text. You could look through, you can work through this example yourself. The table here has all of the input data you need. These are the inputs. The packets when they arrive and what their length are, and you can compute the finish times, and from the finish times the output order in which they should go on the link. Note, if you do that, this queue here on which packets C, E and G arrive has twice weight. So C, E and G. I just put a 2 there to note that they have a 2x bandwidth multiplier. And so if you worked it through, you'd see a few interesting things. You'd be able to work out the output order, make sure that you understood this concept. And you'd also see things happen like packet F will actually get to go before packet D, even though it arrives afterwards, just because of fair queuing, just because of when we're expecting the end times. The end time for this one is longer. So I'll leave you to work through that. So we've now seen weighted fair queuing. Weighted fair queuing has a lot of potential for quality of service. I hope you can imagine how we can use it to just prioritize and protect different flows. By using the per flow queues, we've already provided some protection. So one flow could go berserk and not affect the other flows by adding extra delay and loss to them. And by adjusting the weights, we can also prioritize different flows. If I have a queue with a high weight like 10 and another queue with a low weight like 1, then you can see how I can preferentially favor some traffic. I might, for instance, put Skype traffic in the queue with a weight of 10 and BitTorrent traffic in the queue with a weight of 1. That way the Skype traffic will get to go, will get preference. It's not actually absolute priority, it's just you could send 10 times as many of those packets, or they would drain 10 times as quickly and keep the queue small, so they would probably get sent fast compared to the BitTorrent. Actually, these weights are often more useful than strict priority, because strict priority can starve out a queue if there's ever any higher priority traffic. Okay, but just to wrap up this lecture, let me just say, in case weighted fair queuing sounds a little mysterious, that we haven't yet seen a complete quality of service solution. Weighted fair queuing is a powerful building block, but for any kind of complete solution we need to do a few other things. For instance, we need to determine how to assign packets to different flows. I mean, what is a flow? Could it be a user, an application, or a TCP connection? We will then need to assign different weights to different flows. We need a higher weight for Skype if we want to favor it over BitTorrent, otherwise we haven't necessarily done very much. And also, I'll just point out that actually weighted fair queuing can be difficult to implement at high speed when you have many concurrent flows. So this affects how we might want to use it. We might want a relatively small number of flows. So in some of the next lectures, we'll begin to see ways of building complete solutions using weighted fair queuing to give us quality of service in the internet.